I'm Michael.
I'm Ted.
Right. So, it's all about Apache Drill, so let's drill into that. First, a little question for you. What kind of workloads do you see? Yeah, we know that one. Batch processing, right? HBase, Cassandra, for all that kind of stuff. Stream processing, what kind of streams we can process. IoT, social media streams, whatnot. Of course, very prominent here, search and information retrieval, Elasticsearch, Solr, and so on. But what about interactive ad hoc query at scale? Well, these days we pretty much have these options, not very interactive. And what we want to achieve, where we want to get at, is these guys, right? So talking about interactivity, having a human sitting in front of a box, clicking somewhere and expecting a result within seconds or less, right? So let's have a look at two of the selected use cases we had a look at before we started with that. Imagine you're in a position where you want to track suppliers, so they might have shipments and whatnot, and you have very specific questions there, such as, how did that one supplier, ACM, how did that guy do in the last 24 hours, right? And your data might, in fact, be, good old relational databases and some shipment logs in JSON, for example, right? Another one I call crime detection, fraud detection, whatever. You could imagine that MapReduce style, you generate a kind of heat map here, and the human operator looks at that and sees, ooh, there's something going on here, something reddish, right? And now needs to drill in. That's where the name comes from, right? So you need to understand what is going on in terms of the transactions there to see if the one transaction here is in fact a fraudulent one, right? A couple of requirements we derived from these use cases, and there are many more out there, are that it's essential to being able to support different kinds of backends, different kinds of data stores. We want to be able to have different kinds of query interfaces, really. Obviously, we're dealing with low latency systems, so kind of synergetic to the batch MapReduce style of doing things. We want to be able to support ad hoc queries. Ad hoc queries are really important because the knowledge I have about the data set or the priorities change rapidly. So I need to be able to ask questions in an ad hoc way and hopefully get answers pretty quickly. And of course, as usual, it's got to be scalable and reliable. Something completely different, kind of backdrop where it comes from. We heard today already from Owen regarding Dremel. In 2010, the Google engineers put up that nice research paper and highlighted some of the more interesting pieces of the abstract there. Dremel system is a scalable, interactive, ad hoc query system for read-only nested data. Right? So if you keep that in mind, and that hopefully survives the after party today, then my job is done. Coming back to Drill. So some of the key facts that you might want to consider if that is important for your application. As I said, I tried to point out the Drill design is largely based on Google's Dremel. We aim for SQL 2003 support, reason being that a lot of the deployed BI tools out there natively speak SQL. So you want to be able to plug that in and directly work with that. If you think back of the requirements, the pluggable data sources. So if you want to put Mongo there, fine, Couch, HBase, whatever you have, right? We treat nested data as first-class citizens, right? The schema is optional. So if you have one, if you provide one, that's great. Otherwise, we're trying to explore it and find out how it is. We're going to talk about that in greater detail, I believe. To me personally, what is very important about the overall activity is that it's a true community-driven open source project. So at the end of the day, not Ted or myself, but you guys decide how far we go, how quick we go, and what we can achieve, right? The high-level architecture of Apache Drill, essentially down here you have the data sources, as already mentioned, pretty flexible regarding that. You can support whatever you like there. I'll come back to that in a moment. Here in user land you have a number of, I would say in Apache Hadoop ecosystem, almost standard interfaces, a REST interface, a command line interface. So you have a shell where you can interact with Drill. You have a native API, it's written in Java, and very important, JDBC, ODBC, right? So that's what the end user essentially sees, no matter if it's a necktie programmer or more down-to-earth hacker like we are. Right, so a number of terms I'm going to use, or we're going to use in the following, you might want to remember. The source query, that's something comes in, think SQL, and tells us what we want to do. The logical plan, that's our core piece there, is very, well, an abstract way to say what we want to do in a language agnostic way. The physical plan is actually the plan that says how we want to do things. And the execution plan is all about where we do things in a distributed setup. And that leads us to the query execution. And now you will already benefit from all the terms we just learned. Here comes the source query. We have a parser, open parser API, which means if you come up with a new domain-specific language, whatever, that's fine. We can, just support it right out of the box. Translate whatever comes in here into the logical plan. Looks like JSON, actually is JSON. And if you want to, you can serialize that, externalize it as JSON, and actually, print it out and put it on the wall or whatever. Then comes the optimizer. The interesting part here is that as soon as you run in a distributed mode in a cluster, this optimizer here has a real job to do, right? Trying to figure out how to partition things and spread out things. And then we have the scanner API, and there you can plug in any kind of data source, really. Now, going a bit deeper there in the wire level architecture. So what we have, imagine you have a 4-node cluster, and each of these nodes has a drill bit, that's the kind of process running there locally, and a storage process running, and the entire coordination, the query planning, and so on is actually done distributed, and how that is performed, we're going to talk about that in a minute. And just to remember, each of these drill bits can act as a foreman, can take on a query and drive that entire query process. Number of things here. What we use internally is Curator, which is Netflix Curator, kind of wrapper around Zookeeper. Zookeeper is great, but it's nicer to deal with it through Curator, right? And we use a distributed cache called Hausenblas, and that keeps track of all the metadata, locality information, stuff like that. So as I said, the originating drill bit here is the foreman that receives the query, and that's how it looks like, right? The drill bit where I send in the query, that turns out to be the root of this MultiLevel execution tree. That's one of the innovations introduced by the Google engineers. And then distributes the query down to each of the workers here that actually scan a part of your data and then report back the results there. And you can imagine that this works well when the input data size and the output data size are not equivalent, right? So if you have a huge, like 5, exabytes or whatever of input data, and your result set is also in that same dimension, that might not probably be the best idea. But if the result set, that's, if you think back of the use cases, they're very specific questions and very, the result set then hopefully is rather small compared to the input data. Number of technologies we use here. I remember someone saying in the morning, pointing out Netty, yes, one of the great things. We heavily rely on Optique. Julian Hyde of Pentao is working and contributing on that, almost there. And a number of other things. As I said, Hazelcast, pretty important. Curator as a wrapper around Zookeeper. Yeah, quite some of the good shiny things here. And as I said, or kind of summing up that part, the key features: full SQL support, nested data as first-class citizens, optional schema, and the extensibility points, which, in my understanding, really sets Drill apart from others. Things like, custom operators, UDF. You can do quite a lot of things in the optimizer. Any kind of data source you can plug in via the scanner API. So this is really where Drill shines. Very flexible, very extensible. And yeah, of course, we're working also on the user interfaces. And one question I often get is, how does that compare to Hadoop, or is it a Hadoop killer? No, it's not. It's in a sense, it's complementary. And if you want to learn more about that, the Google BigQuery team put together a very nice white paper. And BigQuery is essentially the user-facing, the service as a software version of Dremel that you can use online. And now I believe it's time to hand over to Ted.
So, what I want to talk about here, basic demo?
Oh, okay. Skip it.
What I want to talk about a bit here are some of the key aspects of extensibility in Drill. As Michael mentioned, one of the unusual characteristics is that you can actually inject code in at several levels. You can provide a SQL parse, or a SQL query, which is parsed to the logical plan, but you can provide the logical plan to Drill to provide, to execute different things. You can also record the physical plan for a particular query, or you might guide the optimizer a little bit until you get a physical plan that you like, and you can reuse that physical plan. You can modify it for your own purposes. So there's deep integration points which are well specified and usable there. I also want to talk a little bit about how that physical plan actually executes, and some of the ways that Drill is able to do this processing with very, very few copies and no more serialization, deserialization overhead than is strictly necessary. I'm going to skip over the basic demo sort of things. But here what you can see, we have here in illegible type on this presenter. I'll try to read it. Of course, it's so small here that there's no way. Let me see if I can adjust. No. Okay, so what we have there is a data source which has a record that describes a particular kind of donut and a few different variants on that. And here we have a logical plan. Again, difficult to read. It starts with a query. It is an operator sequence. Sequence is a higher order function, and it takes functions internally, and it automatically wires those up. Here is one operator, which is a scan operator, and it references a donuts input, which we don't show here, and it has a source, which is interpreted by the scanner, and it selects particular data from there. So we've pushed down a selection into the logical plan, and now we also have then a filter, which has an expression, donuts.ppu less than $2. And this dot here is an extension that is exposed back through this SQL interface, and that allows us to look into hierarchical elements directly. But it also, in an interesting way, when it gets down to the physical plan, lets us look into those hierarchical elements without deserializing the top-level elements. We only deserialize the low-level elements. So that's the logical plan there. And Drill then produces an output of JSON format like that, which are records. Now, the use of JSON here is interesting because this illustrates late schema binding. As you read a JSON file, you have no idea what data you're going to see. You have no idea which fields you're going to see. You have no idea what sort of data you might be executing in there. And Drill is going to handle that, or does handle that right now, in an interesting way. What it does is it reads the input in batches, and potentially in parallel batches. Each batch then has a derived schema if the input is JSON. So on the fly, it invents a schema for this batch. Since this batch is finite and small, we can do that very easily. We don't have to say anything about the future. We just say something about the present, what we see right now. And so if we see integers in a particular field now, we can say that's our schema. If later we see floating point numbers or strings, we can adjust the schema later. And so what then the execution unit does is it takes the schema for the batch, generates code based on that, so that it gets primitive level performance against the batch that we see. If the next batch has the same schema, then all is well. We don't have to regenerate code. If the schema changes, we do regenerate code. Now, for cases where it's not JSON, but where there's a strong schema, we get that schema up front. We do the same sort of operations. It's just that the caching of the generated code works well. So let's go in a little bit more into how that works. So here is the original SQL that we're interested in a particular case. Some unusual characteristics. We might say that this is out of an HBase or an HBase-like table. This happens to be an M7 table, which exposes an HBase API. It could have been HBase. Could have been an Oracle table. We're going to group it by name, which is presumably, although we don't know it yet, a column in this table. And we'll group it there, order it by total sales in a descending order, and do a limit. So the next step transforms this into a logical plan. Here we have the scan. It's now recognized that the storage engine is M7, which invokes the HBase compatible storage scanner. And it has pushed down a little bit into that of the query just to say which table. Very little push down at that point. Then we have an operator which does certain projections. These select different columns. We have an operator here which does segmenting, which is the primitive operation in a group by. Then we have a collapsing aggregate which looks for elements in succeeding records until a flag column, in this case the carryover name there changes, and so it knows to reset the aggregator at that point. And here are the aggregations being done. The aggregations allow a symbolic form, kind of a formula. That formula is of a limited subset of a Java-like language, and that is actually what gets generated into native code on the fly during the execution. This is handled by a specific grammar, so whatever form that you have in your surface form has to be translated slightly there. SQL, for instance, requires almost no transformations. Other languages might require it. If you were translating Cloture or Cascalog or something into this primitive language, you would have to regenerate those expressions. We then do an ordering, which is going to resort the sequence of records that are gotten. And here are the specifications of the ordering. And then we're going to store that data. So this is all the logical plan. This is a very, very tight semantic description of what's happening, but it does not express how the computation will be done. It merely is a restatement of the SQL into the terms specified by the logical language. The physical plan, on the other hand, changes things around a lot. And very commonly for normal sorts of queries that you'd expect to see, the physical plan is much, much simpler than the logical plan. And this is because we can do things like push down the projection operator directly into the scanner. We don't need to pull all the columns out of the M7 table, and so we don't. So we push down that. We also then inject this, which is what's called an exchange node. It's a marker for this is a point where parallelism can occur, where data would be exchanged from one node to another if we were to parallelize groups of operators between exchange nodes. This operator here is the sorting hash aggregate, which does the group by, does the aggregation, and does the final ordering. And it carries all of the aggregation formulas from before back in. And so all of the 3 or so operators in the previous slide, if we go back here, this segment, the collapsing aggregate, and the ordering all collapse into that one physical statement. And this is common that we will have optimized combined operators to do a set of common things. So the exchange defines where we have a parallelism boundary, and all of this down here can then be executed in parallel, except of course the screen, which drives back to the terminal. And that is an inherent serialization point. The boundaries between exchange nodes is a good example of something that is the parallel equivalent of a basic block in normal code generation. So then the execution plan is generated from the physical plan, taking into account where data is actually located, how many nodes that we have to execute on, and it generates fragments. It doesn't generate a single query like we saw in the logical or physical plan. It generates fragments that are then sent to the various nodes. And the fragments include addresses of the place to send output, and so on, and how to interconnect them, and which actual little fragment to execute. The execution unit then takes that tiny fragment and generates code for that. So if we look at how these work, we have leaf nodes, which are doing the raw reading and initial aggregations, or things like that, initial filtering. Then we can pass those back up to intermediate nodes. And the reason that we have multiple intermediates instead of one is that this is not just a tree-based aggregation, but it's DAG-based execution. So the output of a drill program can be much larger, if necessary, than the input, not the normal pyramid-style aggregation where the output is supposed to be small. The intermediate fragments don't actually start until they start receiving data, and all of the transfers here are in the form of those batches that I referred to previously. There's a tight wire level spec for how batches get transferred, but it's not tied to the execution of drill itself. The format is designed, it's in protobufs, but there are large uninterpreted blocks which actually describe the particular columns. This protobuf is also designed specially so that it can be hand interpreted on the fly. The first few bits specify the structure of what's coming up. From there, we can actually direct the socket to off-heap memory so that we can move that data very efficiently. Once it lands there into off-heap memory for a particular execution unit, it stays in that place and in that form. We don't transform that and move it into the heap at all if we can avoid it. What happens instead is we have two things. One is a row-wise bitmap, which is how we encode filter operations. That's stored on the heap and is associated with the current set of records. And that expresses which records are actually active. We do a push-through architecture inside there, so we push the entire set of live columns into a tight native code executor, which does whatever operations are going to happen, updates the filter mask for the set of rows, and only deserializes rows that are necessarily involved in the selection or the operation. And in some cases can even push down selection into the compressed form so that we never deserialize the data at all. On output, the columns that are being used unchanged, if we haven't had any aggregation points inside this execution unit, are copied verbatim out along with any new columns that have been generated in this execution unit. If we did a filtering operation at the output stage, we apply the filtering operation if it results in very few bits being set, or we carry it along for the next stage if it results in most of the records being happened. So the effect of this is we have one copy coming in directly from a socket to off-heap memory, and we have one copy going out for most operations. And that's about as little as you could get. We also have no deserialization of data. We're just carrying along for later units, and we have no deserialization for filter operations that can operate on the compressed form. That means we can minimize deserialization and reserialization of data as it moves through the execution units. And many execution units then can run at full wire speed in and out. This is an unusual characteristic for Java executors. And here's some of these fragments, and we can start seeing how this code generation can happen. Here, for instance, we have a leaf fragment, which is the hash partition sender. So that's part of the group by step where we've got things being sent. And we have a child operator here, which has a mock scanner, which pulls from there. And mostly all it's doing is a projection operation. Here's the original. This one is pulling that many records. That's telling there. Here we go. Here's the actual filtering. And there's the expression applied to that. This is fully cast, fully type managed, because we now know the schema as we generate that. And so we can send from here to our destination RI. That's not shown, but the destinations here would be where we send our data going out. This therefore expresses a very flexible DAG and a very high performance DAG. The optimizer that we use is not complete. It's beginning to produce interesting plans. The place that's very complete right now is the sequel to logical plan. That gets down to nested joins and interesting operations like that. The part that's not very well fleshed out are the physical optimizers right now, but it's a fully general cost-based optimizer, so it has a lot of flexibility that can be applied in those last stages. And it uses the same rule set, it uses the same representations all the way from logical plan through to physical fragments. And so the transformations that work at any given level can be adapted to can work at later levels. This is one of the hardest problems in the system, of course, because we don't have some of the data that we would have in a traditional system. We don't have as much in the way of statistics. We're hoping that the thesis of Dremel, that statistics and that kind of optimization are not as important in large table scan sort of applications, will come through. And so far we do see that most of the optimizations are predominant. You have a particular form of optimization that just totally dominates the others based on the simple statistics that we do have. There's also some early talk in Drill that we could replan as we saw different batches. So the batches themselves would provide early statistics for later optimization. And so there are still hooks for the potential that we would rewrite the DAG on the fly during execution. We don't have that in plan at this time. There will also be a lot of caching of query optimizer steps so that once you've optimized a particular query for a particular data set, you'll have that optimization result available, and you'll also have statistics from previous runs. So you may be allowed to adapt that, or you may want to expose those previously optimized forms to users. This would be a form of query hinting that's much more expressive, you might say, than SQL level query hinting, which is quite difficult in a language where there are no schema or direct indexes to work with. The execution engine itself is provided by a single JVM that heavily threads internally. It uses a very small heap space. The initial prototypes are using heap spaces on the order of 100 or 200 megabytes. This means that GC is a non-issue. It's milliseconds or less of GC overhead when it does happen. And that's because all of the big data that's moving along is off heap. And so we have a few data elements being materialized when the heap arrives, as it comes in. We have a little bit of code generation components being generated at that point, but those then tend to live for the life of the query across many batches. And so the amount of garbage created is very small, and it's created over a period of seconds, which is the processing time for a fairly large set of chunks, which is, again, not a very big load for the GC. We have callbacks for each message sent. That allows us to have detailed metrics as things are coming through. And as I mentioned before, the protocols are heavily designed to minimize copying and SerDes costs. We think that that's based on our experience with other levels in the MapR system. These copying costs are one of the dominant overheads that apply in these high-performance systems. And in fact, these tricks with the protobuf, where we do the direct allocation and redirection of components of the RPC directly into those, are taken directly out of the MapR file system, those techniques. The query setup and fragment runners are all managed via queues and thread pools, and so we inherit the good characteristics of Java at that level. We break the data into batches, and this is how we're able to do this late binding schema. Every batch has its schema, has a collection of fields, and it has particular data types. We have two expressions of the data types. One is at the network level, where we have things like we have things like 4-byte quantity. We have a secondary type system at the execution level itself, where we understand that 4-byte quantity is a small integer instead of a long integer. And that allows us to abstract away the internal data structures, the internal interpretations, so that the network layer doesn't have to change as these internal interpretations of the data change. So if we add new kinds of compression, as we add new kinds of data structures or alternative encodings for things like strings, we don't have to change the network layer or the batching layer or the overall execution framework at all. These value vectors are where we store these things, and these are facades into off-heap byte buffers. This is an exciting and probably reusable construct. It's been designed to be relatively independent of all of the execution environment. I was talking to Stack earlier, and we've been talking at MapR, not necessarily on the drill topic yet, that some of the need for coprocessors in systems like HBase, there are two needs. One is for core committers to write new code for HBase. The other source of need for these coprocessors is for user-level constructs. The user-level constructs are very poorly served right now in HBase by coprocessors. What we need is an arm's length coprocessor that doesn't have visibility into HBase internals. Value vectors, or something very much like them, would provide a very high performance method for building these out of JVM arm's length HBase coprocessors, for instance. They could be used in other applications as well, where the idea of small batched computation would be valuable. And the in-memory of each value vector is well-defined and language agnostic. I'm going to have to hurry up a little bit because I want to give some question asking time. The font is getting smaller as we drill into these systems, as you can tell, and the level of detail is getting higher and higher. But the key point from this slide is that the particular style is that we want to push as much of the work away from the execution framework so that we can solidify that early and drive most of the implementation effort into the creation of a large number of operators. These operators will be of the form small scalar functions, and scalar functions here could operate on complex elements, or they will take the form of things like that collapsing aggregating scanner. They might be special purpose scanners that pull in parts of the query for a particular data source. You could imagine an Oracle scanner could pull in quite a lot of the query. An HBase scanner might be able to pull in some of the scanner or some of the query for some operations. And so that style is of building a large number of operators is key to this design. Another key in terms of performance is that we're sizing all of these batches to be propitious for execution. They're going to be cache size oriented, probably a small submultiple of the L2 cache, so that once a batch lands on a processor, we'll be able to process that extremely fast. And we won't be blowing cache, and we won't be blowing cache for other cores either. Going to skip through. Most of this information is useful, I think, if you're reading these slides offline, as opposed to trying to catch it as it goes whipping by, as I talk faster and faster as the font gets smaller and smaller. And it's got to go faster and higher. So we get higher information content as I speak. Input and output goes via the storage engine interface. One of the interesting things here is that the API for storage engines is partly in the form of optimizer rules. So every scanner, if I write a new scanner for my new whiz-bang data store, what I will give to the system is a set of optimizer rules which tell the system how to give me specialized operators based on the structure of the logical plan. And that gives a huge amount of flexibility and lets us, we've been looking at JSON, we've been looking at HBase, at SQL engines, at Splunk, and at things like the Mongo storage engine as case studies. And this style allows the special purpose qualities of each platform to really shine. And it's the only way we've been able to find that lets the peculiarities of certain storage platforms to be taken advantage of in a general purpose environment. And it turns out it's not terribly hard to do that. You just basically say, if you have a where clause with these variables, I can handle it. And then the optimizer handles rewriting things to give you the sort of things that you need to run well. And you then will be getting a record reader and a record writer sort of calls. And there it is. One of the key things here, and I'm going to let Michael continue on this, is that we want to be a very, very open, very, very aggressively inclusive group. That means that you guys are going to be a big part of this effort. And I'm going to let Michael summarize here.
Thanks a lot, Ted. Right. Current status, we have already some bits here in place you can play around with, basic demo and other things. We're working on a number of things in parallel, SQL support and so on.
Also in May.
Yeah, Back to the Future. And that's probably a very interesting slide for you. So even if you're not a coder, you can actually contribute, and you are encouraged to contribute, coming up with test data, test queries, use case scenarios, or probably even starting the documentation around that. And so I'd really like to encourage people who don't have that coding background, probably in this crowd, that's not that important, but you can, yeah, and you should.
Let me give an example. Ellen, hold your hand up. Ellen has been watching the mailing list and just making notes of important things that have been happening. She attends the weekly Google Hangout and she writes it down, which means at the end of the 3-month period, it's a piece of cake to write the quarterly report. That's a contribution, because otherwise what happens is you get to the end of the 3 months and you go, wow, man, I don't remember what we did. We did a lot. And that doesn't make a very good quarterly report to the board of Apache. So there's a contribution that's decidedly non-codey. She's also been writing some stuff around that, has a contract with O'Reilly to write a book on it, just the beginnings of it. Good examples. People can code, people can provide non-code support for Drill in a lot of ways.
Yeah, a little shout out to our colleagues who have contributed so far in the core. And probably the most important slide, engage. You have a lot of options here, might be on Twitter, good old mailing list. Every Tuesday at 6 o'clock your time here, we have Google Plus Hangouts, where you get the chance to interact with the entire team. And we have a little blog here, reporting on a roughly weekly basis. And I hope we still have a couple of minutes for some questions, right?
All right, let's thank the speaker first. Speakers.